All right, welcome to Tuesday. It is Tuesday. Hey, Steve, good morning, sir. How is Steve today? I think I can do that. There we go. Good morning. Hey, Nihad, welcome. Good to see you, brother. There we go. Good morning. And Alan. Good morning, Alan. Geez, we got the whole crew here today. I Today's Tuesday, Alan, and you know what happens on Tuesday? We do what we can to go live and talk some technical stuff. So that's what we're doing today. I scheduled my IAEI News Live for Article 409. We're going to focus on Article 409 today. Industrial control panels. That ought to be a good discussion. So industrial control panels, I think we have a few challenges with industrial control panels. I believe in 409, maybe not. I thought they were required to be listed. So I don't see a requirement in 409 for an industrial control panel to be listed. They tell you need to be protected by overcurrent protection. They talk about the ratings, but I'm not seeing, I got the short circuit current ratings. That ought to be a good discussion. We'll take a look at SCCR. Short circuit current ratings. You know, I've got a decent video on short current ratings. Not organizations. I got to go to presentations, and I go TD basics, and I've got an SCCR, current limitation, SCCR. There we go, SCCR. There it is. Okay, here we go. It's an afternoon. Oh, excellent. We've got the UK in the house. Why can't I? There you are. So, Aikan Enrico? It's afternoon in the UK. Good afternoon. Good to have you. So we're truly international today. We've got Nihad El Sharif. I don't know, Nihad, are you in, I think you're in Canada now, but I don't know. God only knows where you're at. You could be back in Egypt. I don't know. I have a meeting at noon Eastern, but we'll try to join. I know it's going to be an interesting topic. Absolutely. Alan, your company requires they be built to UL 508A, and we get a field nationally recognized testing laboratory label. Okay, so you get a field evaluation if they are not listed when you purchase them, or do you get them right out of Alan, if you get it out of a 508A shop, those guys and gals will, I think they will list those and label them when they ship. So in my opinion, 508A supplement SB for SCCR is confusion. Is a confusing standard and hard to understand. Yes. And Nihad's in Canada. So I would agree with you. I would agree with you, Alan. When it comes to short circuit current, when it comes to UL 508A, it is maybe that's how we focus a little bit. We'll take a look at 409 today. But determining the short circuit current rating of a piece of equipment, there's a process that typically the designer will follow, and we have our busman group has a an app. It's called Oscar. I'll try to find that. Where is Oscar? Eaton Oscar. I'll just do Busman, OSCAR. Now, Oscar tool. Let's take a look at the Oscar. Yeah, I'll tell you what, Alan. This is a sorry about that. I went on mute. So thanks. You know what? I think it must be. I'm not sure why that happened. Anyway, so Oscar. Let me go back. Oscar is a tool I'll bet nobody knows about out there in who's watching this video, because it was new to me back in the day when I first went down to the Busman group to manage the field application engineers. I can't think of what year that was, but it was a while ago. I learned about this tool, and what it does is it takes that whole mystery out of the 508A standard when you determine short circuit current ratings. And look at this, it's online short circuit assembly rating, Oscar, online short circuit assembly rating. I could never remember that, but it's award winning, and there's over 70,000 individual components and over 30,000 combinations of components. Now, here's the thing. What that means is, when we say combinations, that's like, say you have a power distribution block inside of an industrial control panel. That power distribution block has a short circuit current rating, and the short circuit current rating of that block will depend upon the overcurrent device that is ahead of it. So the way you identify what the actual rating is of that component is by determining what is the upstream overcurrent device. So the process basically, and there's the URL, oscar.busman.com. The process basically is you draw your little one-line diagram that is in your industrial control panel, and it looks at all the components, and you add the manufacturer numbers, you add the information, and you can create your own components, provide the information that the software is looking for, and it will do the analysis and determine what your short circuit current rating is for your assembly. It's freaking awesome, in my opinion. And probably the best kept secret since the recipe for ice. But in any case, there's a library of resources that are in there, and you can add and create your own. Look at this. You can export all of the list of components, and it'll tell you what the short circuit current. It does all the work for you. It takes the mystery, Alan, of that out. Let me get back to this. Boy, I got a lot of comments. In my opinion, UL 508A in my opinion, 508A supplement SB for SECR is confusing. Again, Oscar takes all of that out. Nihad's in Canada. The shop will list and label, but okay. So Alan says the shop will list and label, but we want the whole machine. Oh, so the machine. So you'll have an industrial control panel as part of an overall assembly, and you want that overall assembly. That's smart, actually. That is really smart. Because once you place that piece of equipment in its application, there are implications of that for that. Yep. So if you haven't played with this, I believe that you could probably get, if you talk with your local busman application engineer. And I know you, Alan, that'd be something to tinker with and play with. But we have various 508A shops that are using the tool to determine the short circuit current rating. And I'll tell you, there were some industrial control panels we worked with various customers who basically, yeah, look. So here we go. I'm sorry, I'm interrupting my own self here. In my opinion, 508A supplement. Here's the, you get a free 30-day trial. You can get a free 30-day trial for Oscar. You can sign up for that. And if you want a Eaton Busman field represent a field application engineer, application engineering resources, depending upon where you're at, and I think Alan, I think you're on Cincinnati. I'm not sure if that is. I think that's Joe Pavia's territory. Distributor locator, electronics, busman. I'm not sure. Busman.com. Let's just try Busman. Eaton. www.busman.com. There we go. This is the Busman facility. These guys know short circuit current ratings because that's what they do. I mean, they're fuses. So, they will help anybody get a high short circuit current rating on industrial control panels and all that jazz. And there's got to be a way to contact Busman Series View Toolbox. Man, the Busman has an 800 number too. Man, there's the 2023 code changes. I'll bet you it's in the book. If we look in the book and you look, man, there we go. So here's some of the numbers. If you call this, there it is, 855-287-7626, and ask them about Oscar. And then there's the Busman series. There's their webpage. So in any case, they have some that whole resource of Oscar is absolutely huge in my opinion. So in any case, take the mystery out of 508A supplement for short circuit supplement B, I think it is, and make it happen. All right. Supplement SB. Robert from Omaha is in the house. Morning. A little late, but hey, you're worth the wait. All right. I could not hear anybody. I went on mute. Tom, you lost sound. Tom, your audio's off. Good morning, Robert. Now we can hear you. All right. So we got back in order. I had to unmute myself. Not sure how the heck that happened, but in a case, so let's talk about short circuit current ratings. Close this. So Whoop. A short circuit current rating. I remember a short circuit current rating is not the ability of an overcurrent device to stop the flow of current. It's the ability of a piece of equipment to let fault current pass through it without achieving an unintended rapid disassembly in the field. So it's not an interrupting rating, and in most cases, the short circuit current rating, especially if they're above 10,000 amps for an assembly, you're not going to get above a base number unless you have a protecting overcurrent device ahead of it. So I like this example here because what it shows is if I have the short circuit current rating of that industrial control panel not blow up. You don't want it to blow up. Don't let the smoke out. As manufacturers, we spend a lot of time and money putting smoke in the equipment. Don't let it out. If you see the smoke, you've done harm. So in any case, the fault in these cases are downstream of the piece of the component of the assembly. That assembly has to be able to deliver that fault current. Now, I can reduce the amount of fault current that is delivered by putting a current limiting device so that control panel doesn't actually see the full effect of the fault current. I relate it to bench pressing. I'm sure everybody out there, or most of you, have laid down on a bench at some point and tried to push up weights. So when I think of short circuit current ratings, I think of a good example to relate the differences between an interrupting rating and a short circuit current rating is to understand what short circuit current ratings are. So if you think about the players in this picture, you have the distribution equipment is the weightlifter who is laying on the bench, who is going to be pushing up weight. The magnetic forces that are placed on the electrical distribution equipment in this image are the weights that are placed on the weightlifter. Now, the third piece of the puzzle to understand how much weight this weightlifter can lift without going to the hospital is the OCPD, which is the spotter. The spotter makes sure that the weightlifter does not hurt themselves by lifting too much weight or applying too many reps. So the question always is, who's your spotter? Because the spotter's job is to make sure that the weightlifter doesn't experience too much weight to cause damage to their body. An overcurrent protective device does the same thing for electrical distribution equipment. The OCPD will take this fault current, which we see, it's asymmetrical. That first half cycle is what causes the mechanical forces. The mechanical forces are that first half cycle because of the steepness of the slope of the first half cycle sine wave. The rate of rise is very fast. So you'll get your magnetic forces from the first half cycle, and then you get your heat from the duration of passing current through the equipment. So if I have a current limiting device, I'm just going to focus in on just that first half cycle. Instead of that piece of equipment seeing the complete full first half cycle, which would include that peak current that's way up there, the current limiting device clears in less than a half of a cycle. And I would argue if you have a good current limiting fuse in there, you're probably at a quarter of a cycle, which reduces the time but it also reduces, if you look at the sine wave, you're reducing the peak. So you have less mechanical forces being imposed on the power distribution equipment. Now, I'm going to show an example, what we call this the cable whip example. The circuit layout is I have 45,000 amps of available fault current at the source. I have a device in there that will let one cycle of current flow. So all we have is one complete cycle. If I look back at this image, one cycle, I should be able to get a pencil. One cycle, let me get a pen. One cycle is right there. So this is one cycle of sine wave. What I'm going to show you is an example that has, because of the cable length, 26,000 amps flowing through 90 feet of 2-watt conductor. 90 feet of 2-watt conductor, 26,000 amps, one cycle. Now let's see if I can make this happen. How do I get... There we go. All right, let's see if we can make this happen. I cannot play. So what I'm going to have to do is I'm going to grab the cable whip. I got to do a search real quick for cable whip, or I'll just do SCCR. There we go. Videos and cable whip. One cycle. All right. Let's move that on the side. There we go. And we will move this up here. So this is one cycle of current. And let's see if we can make it happen. All right, so movie. Let's do that one more time. I'm going to do that one more time, but I'm going to unmute the movie. There we go. All right, here we go. Ready? Pretty violent. So, pretty violent example of one cycle of current taking a 2-watt conductor and basically throwing it around the room. Now what I'm going to do, so let's talk about the let through. That first half cycle was 48,100 amps. 48,100 amps. The I squared T energy was 15,700,000. Okay, that was one cycle of clearing time. Now what I'll do is I'm going to take the exact same scenario. We're going to put a current limiting fuse in series with it. And what's going to happen is the current limiting fuse is going to reduce the peak. And we're going to watch first a video of that same example protected by a 200 amp class RK1 fuse, and then we're going to look at the numbers. So let me go back over. Hold on. How do I discard? There we go. Go back over here. Need the cable with video. Hold on, here we go. All right, so now what I want you to do is watch down here at the end of the conductor. I want you to watch at the end of the conductor for the movement, because it's not going to be as violent as the previous image. That was it. Watch down here. It moves ever so slightly. So, let's go back to our PowerPoint. Now remember, we had 45,000 amps, we had 26,000 amps. We saw the video. Now we went from 48,100 amps at that peak, and we reduced that to 10,200 amps, and we went from an I squared T of 15,700,000 down to 127,500. So those are significant changes. Significant changes in let through, which is reflected by the mechanical, and you saw that that cable barely moved, and I squared T, which is the energy. I mean, 15,700,000 down to 127,000. That's just phenomenal. So what you're doing when you provide overcurrent protection for an industrial control panel or any component, you're preventing the damage. You're reducing the magnetic forces that are imposed on that piece of equipment. The spotter's job, if you don't have the right spotter, you could have a disaster in the gym. If you have the right spotter, then you'll protect the equipment. So in this picture, is that your spotter? Or what happens if he says, hey, I got to go hit the restroom, I'll be back in a few, and then this guy says, oh, I got you. I got you covered. One of those guys can handle those weights, another one can't. And the message there is, make sure you pick the right overcurrent protective device to provide the protection, because not all upstream overcurrent protective devices are created equal. Now I'm going to see if this one will work. This one should work, and it's not. Got the same issue. I'll give you a few more examples for SCCR. Here's an example. Me and monitor. This is a industrial. This is like a motor starter. You'll see a motor circuit protector in there with a starter. Once this door goes about 25 feet into the lab, let's take a look at what happens when I exceed the short circuit current rating. I have 65,000 amps. You'll notice that the fault is not inside. I put a what do they call these? Splice bolt down here to just basically cause a direct fault. And let's take a look at what happens. So the door flew off about 25 feet. The motor circuit protector is still in there, but and it's intact. So the motor circuit protector didn't have any issues, and it's tripped. You'll notice the handles in the center. But it wasn't the right spotter for that motor starter. And it blew the door off about 25 feet inside the lab. That's a great example of a severe misapplication of a product. I think I have another good example. That's SCCR3. Let's take a look at what's this one. This is not bad either. This is a good example. So in this case here, this is a pretty old video, but you have a similar application. You've got sort of a motor circuit protector up here, and you've got your starter down here.
Motion. The MCP operates in about 1/2 cycle under a short circuit condition.
So you have a lot of smoke, you've got heat, you've got an unintended rapid disassembly within that enclosure. It's all about how much current you let pass through the equipment. That's all. It's all about how much current passes through the equipment to determine how much damage occurs to the equipment. All right. I got to get better at the short circuit current rating stuff, or my video. The codecs aren't working for some reason. I'm not sure what it is. So when you're dealing with short circuit current ratings of equipment, you have to know your rating of the equipment. You have to know your available fault current at that equipment. And you need to make sure that the rating exceeds the available fault currents. It's not rocket science. Alan, what did you say? Human got a bruise but was not cooked. All right, so the motor circuit protector and the contactor both need correct SCCRs. So here's the thing, Alan. Your motor circuit protector has to have an interrupting rating. Remember, overcurrent protected devices do not have a short circuit current rating. Overcurrent protective devices like fuses and circuit breakers, and I would throw a motor circuit protector in there, things like that. Those have interrupting ratings because they stop the flow of current. What needs to happen is, here's what needs to happen. Let me find that sine wave. Remember the sine wave, okay? If your overcurrent protective device lets more than a quarter cycle through. Let's say your overcurrent protective device takes 1 cycle to clear. Your piece of equipment is going to see the full first half cycle. If your overcurrent protective device, let me do this. Let's bring this up this way. If your overcurrent protective device, I am going to copy this page. Where's it at? Here it is, Control CV. Let's create another page. Let's say that your overcurrent protective device somewhere stops. Now I've increased the time, but I've also increased the peak, right? So I've let more current through to the load and passing through the component. If I take a little bit more time to clear, so now I'm letting even more energy through. So your upstream overcurrent protective device, clearing time, and speed of action based upon the fault current will tell you what your component sees. Now, the ability of the component, the way the construction is, will determine how much magnetic forces it takes to damage it. So that peak current makes a big difference. If I had, say, busway, for example, where I just had a solid copper conductor and the weakest link is probably the termination points, I might be able to take more let go. I may be able to have a slower device upstream than, say, a GFCI receptacle, right? Or a motor starter that has much more, has less copper, has more moving parts, is more dainty, so to speak, right? So the device itself has a capability, has a substance to it. The overcurrent protected device is basically the speed at which it can clear the fault. If, I'm going to look and see, I know we have a table in 508A. There's the table. So this table in 508A gives you different short circuit current ratings. Now, a circuit breaker doesn't have a short circuit current rating. It's an interrupting rating. Meters, current shunts, fuse holders, 10,000 amps. This is without having an overcurrent protected device upstream. They tell you what a fuse holder can handle, what auxiliary devices, what switches, motor controllers, motor sockets. There's your receptacle type GFCIs. There's a standard receptacle other than a GFCI, supplementary protectors, switch units, terminal blocks or power distribution blocks. All of the different components that you'll find in an industrial control cabinet are going to have a construction that will dictate how much current it can handle, how much magnetic force it can handle passing through it. Alan says, true, but I sometimes use the terms interchangeably. Yeah, and we all do. I mean, I've had people ask me, what's the short circuit current rating of that breaker? And I know what they mean, and I'll just answer it. I won't go, oh, that's not a short circuit current rating, that's an interrupting rating. Because it's, if I'm in a class, I'll do that. But I just answer the question because I know what they're talking about. But we all will use those terms interchangeably. Proof positive of why the critical point of maintenance. Oh, yeah, maintenance is critical. And anytime you change a component inside of an assembly, you may say, look, my power distribution block, I don't have enough termination points. I'm going to put a longer termination block in there. terminal block. You need to understand which terminal block you're using and what is the short circuit current rating of that terminal block. You just don't pick one. Terminal blocks. Oh, give me a manufacturer who makes terminal blocks. I don't know. Phoenix Contact. They make terminal blocks, right? So let's just take a look out at Phoenix Contact's website. Miniature micro blocks. I don't know. Let's just pick one. Support and resources. Over e-business. Contact. Find product expert. Engineering data for control cabinet building. Let's take a look at that. Autodesk, ePlan. I'm looking for catalog info. That's a digital business. Hold on. Products. Connectors, terminal blocks. Power dish, PCB terminal blocks and PCB connectors. Let's try that. No, that's a power circuit board. I was there. And new product overview. Let me go back. Terminal blocks. Let's go back to Phoenix again. Get to the right web page. All right. Let's just look hybrid. I'm just trying to pick a terminal block to go look at the technical data. Feed through terminal blocks, micro terminal blocks. Let's just look at those. Technical data, electrical properties, maximum power dissipation, product properties, number of rows, potentials, cylindricals. I'm just trying to find a short circuit. Electrical tests. Test passed. There's a voltage. Temperature rise, mounting, environmental, mechanical test. I don't see an SCCR in here at all. Let's just do SCCR. Nope. Terminal block, SCCR. Terminal block, automation direct, Phoenix high fault current, short circuit current ratings. There we go. Just downloaded a file. Let's take a look at what it says. All right, so this one looks at a SCCR combined with Siemens breakers. So they're calling out a specific manufacturer in this case. They're referencing 49508A. Tested components, so you can test these. See, there's an SCCR of 100,000 for years. Tested combination terminal blocks with fuses have been available for the clip line complete system. So they test these together with an SCCR of 100,000 amps. They generally exceed the usual maximum possible fault currents at the installation sites. They got 1059 for terminal blocks. Phoenix modular terminal blocks increases reliability. The terminal blocks have been tested in combination with fuses per UL 248 with an SCCR of 100,000 amps. So you're going to get the highest short circuit current ratings from a current limiting type of device like a fuse because of how fast they operate. New additions are the tested combinations with circuit breakers with a high fault SCCR of 50 to 65,000 amps. It's going to be less than a fuse because a circuit breaker takes a little bit more time and lets more current through, which puts more stress on the component. And depending upon the construction of the component, the construction will tell you how much current and time it will let pass through. All right. So, and they'll typically look, there's your catalog numbers, there is your manufacturer and the type of the overcurrent protected device and the amps and the available short circuit current rating and the voltages. So when you look at components, when you think about the short circuit current rating of equipment, you will have to understand how components work together. All right. Oh man, Alan, old versions of UL 508. Old versions of UL 508A supplements B did not allow engineers to use the let-through current graphs. Right, so most of them are tested pairs. And I'll tell you, if you look, as you look in different manufacturers, if you look at various components, they will tell you what the upstream overcurrent devices need to be for a short circuit current rating, what you need. So I'm looking for, here's another company. I'm just looking for a company who carries, and I like looking at terminal blocks just because a lot of people think, wow, these things are very substantial and whatnot. And they can, and I don't have to worry about the overcurrent protective device that's ahead of it, but you absolutely do. And the information in their catalogs will tell you what you need for protecting those overcurrent the components. And I'm just looking, and I'm looking at a manufacturer now. I'm gonna show you the screen. Power distribution blocks with SCR and feeder spacing. The requirements of the National Electrical and UL 508A now require many electrical panels to carry a short circuit current rating. Analyzing the SCR of an individual components and overcurrent protection devices is a method to determine. Marathon. This is Marathon. Recognized listed power blocks have been used in electrical control. These blocks have been tested and approved for a higher SCCR. The higher ratings are based on proper wire sizes and the appropriate short circuit protective device, fuses or circuit breakers. And they make that in bold because it's a test, and the clearing time is a critical component for the application of this equipment. And you can have for power distribution blocks that don't have a specific, no additional testing, you're grandfathered in with 10,000 amps. So if you have a power distribution block in your assembly and you need 65K, and you have a power distribution block like this in your assembly, then because if you don't have a pair, if you don't have evidence, if you don't have data from the manufacturer that says here is the overcurrent protective device upstream that you need, and this is the short circuit current rating above 10,000 amps, then you have to assume it is 10,000 amps because you don't have that additional data. So that 10,000 amp short circuit current rating on that power distribution blocks limits the entire assembly to 10,000 amps because it's your weakest link. If it is your weakest link, if you have a receptacle, let's say you have a receptacle SCCR. If you go to a receptacle, I'm going to go to, I don't know, we'll just do an Eaton receptacles. Eaton short circuit current ratings. Receptacle. I'm just going to look at a receptacle, and we're going to download technical data. Duplex receptacle. Okay, let's take a look at a duplex receptacle. There should be in here somewhere the short circuit current rating. Electrical spec withstands 2,000 volts. Current interrupting at full rated current. Terminal accommodations, overload 100%. What is the short circuit rating? Control F, SCCR. There's no short. I'm not finding anything. Let's try a different receptacle. Let's try spec grade. See what this one says. I hear comments coming in. Hold on. Those are all the different types of receptacles. PVC. These are all the type of body materials. Spec grade, standard grade. None of these are ratings. None of those are ratings. This is all just sales information. Commercial grade, straight place duplex. 3-pole. I'm not seeing it in... All right, here we go. What's this say? That environmental, electrical, dielectric withstand, current interrupting. I'm not sure what that is because it does not interrupt. Temperature rise, dielectric voltage. There's the size of the conductors. I'm not seeing anything in here on short circuit current ratings. So let's do this. Let's try Hubble. Hubble receptacle. We'll throw rating in there too. Ratings. Let's try Hubble. Straight blade receptacles. Let's take a look at just a trade select view. Application, RoHS, materials, dimensions, ampere rating, connectivity, current rating, voltage rating, wattage. It's like nobody puts in the information. Here's the specs. Let's take a look at a spec. Nobody puts the short circuit current rating of a receptacle in their receptacles. Come on, people. They don't either. All right, so let's look at a GFCI. Eaton GFCI receptacle. All right. Let's take a look at Eaton GFCI receptacles. Ground fault circuit interrupters. And let's go to resources. Arrowheart GFCI receptacle with a night light. Wow. All right, let's see if we have anything in here. 30 tamper resistant. Electrical, dielectric, frequency, short circuit testing, meets and exceeds 10,000 amps. All right, so at least this one has a short circuit test. So when you get to a device like a GFCI, because there's contacts in there, this tells you it has a 10 kA, and it should say short circuit current rating, but they call it a short circuit testing. Meets and exceeds 10,000 amps. I don't know what exceeds 10,000 amps means. It has a 10,000 amp short circuit current rating. Probably because when you test the GFCI, it's tested with a fuse ahead of it. And fuse has a very fast clearing time, so that's how they get the 10,000 amps. Let's see what others say. Hubble GFCI receptacle rating. Spec guide. Let's take a look. I'm just going to the first one. That's a GFCI. It's not a receptacle, but it is a GFCI. Let's take a look at specs, wiring. Let's see if they have, they don't, that's wiring. What about this one? Catalog. Control F, SCCR. Let's see if they use. Let's try short circuit. Nope. Well, that's the full catalog. Literature. I thought for sure they would have, I guess they don't, resources and downloads. Catalog, industrial, commercial products. So no, I don't see, anyway, I'm sure that they have a short circuit current rating. It's just a matter of finding the right document. All right. Okay, hold on. Man, you guys were chatting it up. Old versions, People forget that OCPD rating amps and equivalent SCCR are two separate things. Yeah, that's exactly right, Robert. Hey, Jeffrey Romani. Love your dedication to the vocation as a person. Rebuild the grid, times of disasters. Let's keep it up. Amen, brother. Steve Spiker. Okay, misapplied OCPDs are abundant out there in the field. Other equipment without correct fuse holders, personnel qualified but unfamiliar with arc fault, available fault current, AFC, available fault current, SCCR, amps interrupting currents, AIR, UL 508A, 110.10. Absolutely. Let's talk, Eaton heavy duty safety switches. All right. Okay. Non-fused heavy duty switch has a 10,000 amp SCCR unless installed downstream of a current limiting fuse. That is correct, Alan. Then you can have 2,000 amps. So let's do this. Eaton heavy duty safety switch. I'm just going to bring that up while we're chatting. Okay. A fused heavy-duty safety switch with a current limiting fuse always has a 2,000 amp, 200,000 amp. You are probably right. You are probably right. I would not argue against that. Hey, Willie, yes. It's 9:15. I think I got to watch my clock here. All right. All right. Why does the withstand rating of the conductors get overlooked? The conductors see the same heat and mechanical forces, yet they're never... You know what? Okay, so here's my thoughts on that, Robert. The National Electrical Code, when it comes to conductors, we are basically going off of the NEC. The NEC has done all of that for us. We pick a conductor, we determine the load, we determine the ampacity of the conductor to supply the load. We pick the conductor. Then we pick an overcurrent protective device, and the NEC tells us how to get that done. Small conductors, we have in Article 240, we have guidance for short circuit protection of conductors in Article 240, and they'll tell you that small conductors need specific overcurrent protective devices to provide the short circuit protection. That's why you see the requirements in that in Article 240. I believe that is 240. I think 6. I don't know why I'm thinking 6. It could be 4. Article 240.4, protection of conductors. Could be 4, and it is 4. So it's, if you look at Article 240 and you go to 240.4, you'll see where they say small conductors, unless specifically permitted in E through G, the overcurrent protection shall not exceed that required by 240.4 D1 through D8 after any correction factors for ambient temperature and number of conductors have been applied. So this gives the rules for, and the focus here is not overload protection of those conductors, it's short circuit protection of those conductors. So I would say the reason we don't necessarily talk about it all the time is because we're just following the code for proper protection of conductors. That's my story, and I'm sticking to it. Steve. Steve says, yes, Alan, this area of concern has weakness out there in the field. Engineers hired in establishments without electrical background because of their electronics background. Ooh, acting as AHJs. You know what? I always said, just because you have a degree, just because you have those 2 letters, PE, behind your name does not mean you are the expert, right? So as a professional engineer, we have to make sure that we work in our area of expertise and realize when we're getting out of that area of expertise, right? So very good point, guys. Very good point. So the insulation. So here's my thought process on the insulation, Robert. Insulation damage is going to occur because of heat. Heat is generated from duration. So when you get a conductor to damage the insulation on a conductor, you need heat over a period of time. Now, a short circuit currents for short periods of time can generate a lot of heat, no doubt. But I think the biggest concern for damaging the insulation on a conductor is overload and not properly adjusting the ampacity of the conductor. So you have the solid or the stranded conductors themselves, and then you have the insulation that's around the outside. The insulation is going to be damaged physically because I cut it with a razor blade knife or scraped it along whatever when I was pulling it out of the raceway in the conduit, or heat, which is a duration of an overload. And I would argue not adjusting the ampacity of that conductor correctly for the environment is one of your concerns. So that's my story there, and I'm sticking to it. Trying to limit the unintended rapid disassembly parts in the field. Absolutely. David Englehart, good morning. Where does it say the minimum? Ooh. Short circuit current rating in 508A, David. Now, what you don't ask is what is the component, but in 508A, there's a table. I'm not sure what the table number is. You know what? Let's do this. Here's what I'm going to do. I'm going straight to the horse. We're going to go to UL 508. Now, I'm not sure what edition this is. I have got an older edition, I'm sure. But I know there is a. I'll tell you the edition I am on. Shouldn't there be a date? This was downloaded in 2016. So this is an older edition and downloaded in 2016. But that table will be here. How they say guaranteed. But let me find it. I am going to find the table, and I'm going very slowly. SCCR. I'm going to search up short circuit. Short circuit. I could have swore it was in 508A. If I hit enter, short circuit current rating of the capacitor. Whoop. Nope, that's not it. Short circuit for each of the panels. Short circuit current rating. There's the marking requirements for short circuit current industrial control panels. Here it is. Table SB 4.1. There we go. And I can't remember who asked the question. David Englehart. There you are, David. Where does it say the minimum SCCR is to be 5K? That is the basic question. So if you look in an industrial control panel, assumed maximum short circuit current rating for unmarked components. And I have a problem with a circuit breaker because circuit breakers do not have a short circuit current rating. Neither do fuses, but fuse holders do. There's 10K for fuse holders. There's motor controllers. There's receptacle. There's receptacle GFCI type is 2K. Receptacle other than a GFCI is 10K. Terminal block or power distribution block 10K. And multi-point interconnection wire assembly 5K. Short circuit current rating is not required when connected via a current transformer, blah, 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 blah. So that's that one. The other one we can look at, David, is, I think UL 98 is switches, which we were just talking about. Switches, short circuit withstand tests. They call them withstand, but that's a short circuit current rating. Okay, let's just see if there's anything in here that mentions the 10,000 amp number. There it is. So here is an example. This one here is in 7.6. Switches rated higher than 10,000 amps, short circuit current, shall comply with the close open test requirements. So there's an indication right in that example of where the standard says it treats something that is rated higher than 10,000 amps separately. I'm going to continue to look. Everything, okay, even here's 7.7, which is the short circuit withstand test. The following switches shall be subjected. Switches rated higher than 10,000 amps. So there is no test for 10,000 amps and below. Only when you go above 10,000 amps are you required to do a short circuit current test. Unfused switches having 5,000, 7,500, or 10,000 amp short circuit current rating and marked for use with overcurrent protective devices so it's got to be marked for use with an overcurrent protective device, having a continuous current rating greater than that of the switch. Switches with design technologies other than knife blades and a short circuit current rating of 10,000 amps or less. The 5,000 and 7,500 amp levels are applicable only to combinations of the switch and circuit breakers. Switches rated 10,000 amps and below available volt current, a previously untested sample shall be permitted. So they established that number, that line in the sand, basically, of 10,000 amps. Now, if I go to, let's go to an Eaton disconnect switch. I did have that up. I believe I did. Yep, there's your Eaton switching devices. So these are your Eaton, let's just do a quick search for short circuit. Short circuit current ratings of non-fusible switches. The UL listed short circuit current ratings for Eaton non-fusible switches are based on the switches being properly protected by overcurrent protective devices. For applications that require a UL listed short circuit current rating of 10,000 amps or less, an Eaton non-fusible switch must be properly protected by any overcurrent protective device. So it's not that you don't need a overcurrent protective device. You can use any overcurrent protective device upstream. Fuse or a circuit breaker, any catalog number, any manufacturer. For applications that require a UL listed short circuit current rating of greater than 10,000 amps, I'm right here now, an Eaton non-fusible switch must be properly protected by the appropriate class and size fuse that is noted. Otherwise, the non-fusible switch must be replaced with an Eaton fusible switch. So if you come down here, here's your safety switch ampere rating, 30 and 60, maximum system voltage, 600, circuit breaker maximum short circuit current rating, 25,000, circuit breaker maximum, this is maximum, I think that's interrupting rating, that's not short circuit current rating. Here we go. Down here's a table here that tells you for the maximum short circuit current rating of 10,000 amps, your upstream device can be a class H or class K fuse and any circuit breaker. a maximum short circuit current rating of 14,000 amps. I can do an FTB breaker, specific breaker. 18,000 amps, I test with an FD-EGE breaker. 25,000 amps, you test with an FD blah, blah, blah. Up to 2,000 amps, 200,000 amps, there's your fuses RT, J, and L. So that has to be protecting. Those upstream devices are your spotters. That's your spotter, making sure that that non-fusible safety switch is protected. All right? And there's all the fuse information and all that jazz. So the key thing to remember when you're dealing with industrial control panels, there are, and all the different components or fusible disconnect switches, things like that, there are some default values that you just have to be careful with. And good question, David. Hopefully I gave you some guidance on that. Morning, David. This is a great subject. Yay, Robert from Omaha. Alan Burstein. For receptacles, I guess we use the UL508A default receptacle SCCR. Remember, in 508, the default for a standard receptacle is 10,000. But for a GFCI, it's 2,000. You can have a GFCI that is 10,000 amps if you find one from the manufacturer. All right. Check UL product safety standard for SCCR. Oh, yeah, I can do that too. Steve, David, default 5K in table SB 4.1 of 508. Yep. I thought I saw this in the NEC somewhere. NEC has a minimum interrupting rating for a circuit breaker and a fuse. And that should be in Article 240, David. Probably in the general requirements. I think it's a 240 thing. Control F. 5,000. Is it 5KA? If I do a search, marking, current limiting, that's 240.6, fixture wires. There is a minimum interrupting rating somewhere. I thought it was in Article 240, 10,000. I could have swore it was in Article 240. Wow. I'm not sure, guys. I'm not sure. Robert, did you find it? I can't. Oh, man. I know interrupting rating. 240.60 and 240.80. So 240.60 and 240.80. 240.80 method of operation. No. I'm in the 2023 code and I'm not seeing it in 240.80. Here it is. All right. 240.83 marking. It's in the marking requirements. So here we go. Every circuit breaker having an interrupting rating other than 5,000 amps shall have its interrupting rating shown on the breaker. The interrupting rating shall not be required to be marked on circuit breakers used for supplementary protection. So circuit breakers is 5,000 amps, and I'm sure there is a marking requirement in fuses. That is 240.83. So fuses is covered under... I'm going to look for marking requirements for fuses. Type S Edison-based general 240.50. Nope. Disconnecting and guarding, enclosures, location. I'm not sure where fuses, plug fuses. Oh, that's plug fuses. Cartridge. It's got to be in, there it is. Marking for 240.60. 240.60 Charlie. Marking. Fuses shall be plainly marked either by printing of the fuse barrel or a label attached by the fuse barrel, interrupting rating where other than 10,000 amps. So that's where those two numbers come from. Good questions. Good questions. Where is Steve Specker? Okay, Alan, for conductors, in a short circuit study, the coordination study, we pick protective devices to protect the conductors from overheating and withstand damage. That's right. We'll plot the damage curve, right? We'll plot the damage curve, but if you're following the code, that protection of those conductors is inherent. I'm going out on that limb, Alan. If anybody disagrees with that, I'd love to know, if you do disagree, that if I simply follow the code, I'm going to provide overload and short circuit protection for my conductors that I select based upon the NEC. It's when I start to engineer a solution, and when I'm plotting the damage curves, if I'm pushing the limits of the conductor itself, that's when I really have to start thinking about the short circuit current rating. I need to think about the copper, either the copper vaporizing or annealing, and then the insulation melting. So, all right, I like it. Time current characteristic curves, TCCs, time current characteristic drip curves. What about 250.122, right at the bottom of the table saying equipment grounding conductors may need to be sized larger than the table to meet 250.4A5. So 250.1. So here's the thing with don't even get me on 250. 250.122. Here's my issue with 250.122. Robert, I don't know of any reason why I would increase the size of my equipment grounding conductor outside of what the code tells you. The code tells you in 250.122 250.122 says if ungrounded conductors are increased in size for any reason, if you go out to NFPA link, 250.122 says if ungrounded conductors are increased in size for any reason other than as required in 310.15b or 310.15c, that's the number of conductors in a raceway, and then the environmental stuff. Wire type equipment grounding conductors shall be increased in size proportionally to increase in circular mills. But here's my problem. And it says, equipment grounding conductors shall be permitted to be sized by a qualified person to provide an effective ground fault current path in accordance with 250.4A5 or B4. So if I could look at 250.4A5, electrical equipment and wiring and other electrically conductive material likely to become energized shall be installed in a manner that creates a low impedance, facilitating the operation of overcurrent device or the ground detector. So if I have a 200 amp circuit, my ground fault current would have to be less than 200 amps. As long as my ground fault current is greater than 200 amps, I will open the overcurrent device. I don't know what scenario that you would have a long enough conductor that would get you less than 200 amps on a 200 amp circuit. I don't know how long it would have to freaking be. You'd have voltage drop issues by the time you got to a ground fault current that would not open that circuit breaker. So all you've got to do is calculate the ground fault current and make sure it's greater than whatever the overcurrent device is upstream. And then if you say, well, shoot, it's not, Let's say that it's, I don't know, say it's 100 amps on a 200 amp circuit. Put ground fault protection of equipment in, 30 milliamp. You could put 100 milliamp GFPE. I'm protecting the equipment grounding conductor. I'm not going to worry about heat, because if my overcurrent protective device is protecting an insulated conductor from heat, and I've got less than 200 amps flowing, I'm not going to overheat the conductor because the conductor is rated to handle 200. So if it's less than 200 amps, I'm not worried about heat whatsoever. But this says that electrical equipment and wiring and other electrically conductive material likely to become energized shall be installed in a manner that creates a low impedance circuit, facilitating the operation of the overcurrent device or ground detector for impedance grounded systems. It shall be capable of safely carrying the maximum ground fault current likely to be imposed on it from any point on the wiring system where a ground fault occurs to the electrical supply source. So it shall be capable of safely carrying. So if I'm less than 200 amps, even if I'm less than 200 amps, I'm not going to overheat the conductor. I'm able to carry that current safely. And I'm not going to damage or anneal or vaporize the equipment grounding conductor. So 250.485 is your saving grace when it comes to the equipment grounding conductor. I don't know of any reason, I can't think of an application where I would say I would have to meet 250.122, I need to increase my equipment grounding conductor size. I mean, now, might I need to increase the equipment? I can't. No, I cannot think of any reason. I can't think of a reason. I would love to see an application where you'd say, look, Tom, this application, you're increasing the equipment grounding conductor size. Not just to meet 250.122 that just says, hey, I increased the equipment grounding. How do you not meet 250.4? It's going to safely carry the ground fault currents. I don't know. Anyway, that's my soapbox. I think, David, it's somewhere maybe in an annex or table in the NAC, but I can't remember that. I'm not sure what you were looking for, David. Oh. SOARS has the calculation for withstand rating. That's right. SOARS grounding will give you the equations. There's the underdonk method or something like that. So you have the short circuit. That's the annealing. You have to worry about annealing of the copper, and you have to worry about vaporizing the copper, and then you have to worry about damaging the insulation from heat. There's your 240.60 for voltage for fuses, 5,000 amps for a circuit breaker if not marked, and 10,000 amps for fuses if not marked otherwise. Yep. I found it interesting that EVSE already calculated the 125%. Yep. It's continuous load. I'm not sure what you mean by found it interesting. I find everything interesting in the code. 250.40A5 says you need to provide an intentionally constructed for maximum available fault current. 250.4A5. 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 I'm curious now. And I'm going to have to run 250.4A5. Effective ground fault. Electrical equipment and wiring and other electrically conductive material likely to become energized shall be installed in a manner that creates low impedance circuit, facilitating the operation of the overcurrent device or ground detector for impedance grounded systems. It shall be capable of safely carrying the maximum ground fault current likely to be imposed on it from any point on the wiring system where a ground fault occurs to the electric supply source. The earth shall not be considered. So it says you need to provide an intentionally constructed for maximum available fault current. It's ground fault current, not short circuit. Maximum available fault current is a defined term, but it's the maximum ground fault current likely to be imposed on it. So it has to be capable of safely carrying it. And if it's a bare copper conductor, if the ungrounded conductors that have insulation on it are protected by the overcurrent device, how am I not going to protect the equipment grounding conductor, which is bare copper conductor? I'm going to. If I'm protecting an insulated conductor, I sure as heck am going to protect a bare uninsulated conductor. So I'm not worried about the overcurrent protection. If you're worried that you're not going to trip the overcurrent device, well, if it's a 200 amp breaker, you need 200 amps worth of ground fault. And if you have 30 milliamp GFPE, you need at least greater than 30 milliamps to protect the equipment grounding conductor. So I don't know. Nihad, in the case of using a Class D special purpose GFCI, you may have to increase the size of the equipment grounding conductor to limit the voltage to ground. Yes, very good point, Nihad. For a Class D type of device, we rely on the equipment grounding conductor size to ensure the proper voltage across a person. Yep. So that's not in here. So that would be a great public input for next cycle for Article 250 somewhere. Nihad, put that on the list, buddy. Willie Snyder, the manufacturer already knows for 125% there's no need to adjust the branch circuit. The manufacturer already knows for 125%. Already allows for 125%, so there's no need to adjust the branch circuit. So you're saying that the manufacturer of the EV charger allows, but remember there's two ends to every circuit, right, Willie? It's not just about the charger. It's also about the overcurrent device that's supplying power to the charger. So the manufacturer of the charger has built that in, but what about the overcurrent device upstream? And we don't pick the overcurrent device upstream until we size the conductor. So you need to know if it's a continuous current or not. I'd need a section reference to be able to answer or even discuss that one, but I'm not seeing a section that's referenced. All right, everybody, listen. It went longer than what I wanted to, but it was great. I enjoyed the discussion. We noodled around the code a little bit. We noodled in around short circuit current ratings. We talked about different components and industrial control panels. We're going to continue our discussion. We're going to get into Article 409 today at 12 o'clock Eastern on IAEI's YouTube site. I put the link down below. Please check it out, and we will see you again at 12 o'clock Eastern. So thanks for tuning in. I appreciate everybody dialing in and having some fun and having a good discussion. All right? Thank you, Robert. Thank you, Nihad. Thank you, Willie Snyder. Thanks, Steve. Alan Burstein. David Englehart. Steve Spiker. Spiker. And the crew, Robert from Omaha. Take care. We'll see you at 12 o'clock Eastern.